everyone. Today we have here in the VLab meeting seminar Martin Zika from Charles University, and he will speak about NQP manifolds and dg-Lagrangian relations. Welcome, Martin. You can start when you.
Thank you for the introduction, and thank you for the invitation. It's a great pleasure to be here and talk to you. So let me share the screen. Okay, so I hope you can see the presentation now. Okay, great. So let me just close some of the pop-ups.
Yes.
Yeah, so... Okay, so can you see it now correctly?
Yes.
Great, okay. So I would like to tell you this story of graded symplectic geometry and how graded symplectic manifolds generalize symplectic manifolds, and how certain theorems and sort of pieces of folk knowledge of the last 20 years glued together. Okay, so I will start with the definition of NQP manifolds, and I will very briefly say how they how a motivation comes from physics, from gauge theories, and then I will go on to the first very interesting example, which is generalized geometry. So that's yeah, this is the maybe the main part of the talk, which is the review of the theorem of Dmitry Roytenberg. It showed that generalized geometry, which is the study of Courant algebroids, somehow coincides with studying NQP manifolds of degree 2. So there's this theorem which says that those structures are in a one-to-one correspondence. And in the last part of this talk, I will show you, I will sketch how we can extend this this one-to-one relationship into a equivalence of categories. Okay, so as to graded geometry and graded symplectic geometry, let me start with this big picture. So at first, very briefly and vaguely, on the right-hand side, we have. Can you see my mouse pointer or not?
Yes.
Yes. Okay, great. Okay, so on the right-hand side, we have NQP manifolds of degree.
So I have a question before you start, which is like, because you have put at the end the woodwork categories and so on. I'm very intrigued by those. So do you completely understand what they do before? Like, this is a question for the end, but I do it at the beginning.
Well, actually, in fact, I only use them in a very simple way, and I haven't really done any like serious research with that actually Warhammer and Woodward did. So
it's a kind of black box for you. I mean, right?
Yeah, it's just a. I'm just using the basic idea, and I'm not.
Okay.
Yeah,
okay.
The basic construction.
Thank you. I'm looking forward to this. Thank you.
Okay, so here we have graded or NQP manifolds of degree 0, 1, and 2. They come in those towers, those sequences, and during this talk, I will sketch how they encode in degree 0 just symplectic geometry on this base manifold M0, Poisson geometry on M0, where this M1 part can be thought of as the cotangent bundle with some appropriate degree shifts in the fiber coordinates, and the degree 2 part, which is the first really interesting part, is generalized geometry, which is the study of Courant algebroids. Those are vector bundles with some extra structure, and here we will basically consider this M1 part to be the total space of this vector bundle. Yeah, I will also tell you what is M2 part is, and how it all fits together, how these correspondences of say objects translate to the categorical or to correspondences of morphisms. So let me defining NQP manifold. So an N manifold, by this N I mean non-negatively graded, of degree N is a graded local ringed space M over M0, where M0 is a real smooth manifold, which is not graded. It's an ordinary manifold. And by graded local ringed space, I mean that we have this base manifold M0 equipped with a structure sheaf. So a bunch of say functions on neighborhoods of this base manifold, and it's given by locally. It's given by this local model. So the structure sheaf, the local model on this U, this open set of the base manifold M0, is given as this tensor product. It's just the functions on the base manifold, or sorry, this should be U, not M0, but it's the functions on U, which are just functions on the local functions on the ordinary smooth manifolds, and those serve as coefficients, which multiply this the more interesting part, which is the graded symmetric algebra over this vector space V. And this vector space V is a graded vector space. It's again non-negatively graded, and it's composed of parts that acquire degree from 1 to n. So this degree n of the n manifold is the degree of say the highest degree coordinate, or highest degree generator of this local algebra. So this whole thing, the local ring is actually also an algebra. It's a real associative algebra, which is non-negatively graded and graded symmetric. So it's symmetric up to a sign. And this structure comes in the form of this tower, where M0 is just the base manifold. Now M1 is the n manifold, where we only consider the part, the degree 1 part of this vector space V. So this would be an n manifold of degree 1, and we can add more and more parts of this vector space. We can add more and more generators, or say homogeneous basis elements of this vector space V. And the highest term here is the one where the highest coordinate is of degree n, which is the whole n manifold. So these are the towers that I showed in the first picture. And now we can add some structure. So an NQP manifold is a differential symplectic n manifold. So this okay, first this Q stands for this cohomological.
Sorry, may I ask a question?
Yeah, sure.
What are the maps in the tower?
Mm-hmm. Yeah, that's a good question. I kind of didn't say anything. I kind of hit it. They, by those maps, I mean the maps of the structure sheaves, which go in the other direction. So if we take just the structure sheaf of M0, that's just the structure sheaf of the base manifold. Now M1, that's a structure sheaf where the local model also has those degree 1 generators, and there's an obvious inclusion of this structure sheaf into the larger one. So those maps that go, so the one that goes from M1 to M0 can be understood or should be defined as actually the map of the structure sheaves, which includes the smaller structure sheaf into the larger one. And for example, in this M1 M0 part, it can be shown that you can always model it as a vector bundle projection. Now those higher arrows, which go say from M2 to M1, that would be something similar, but the structure group wouldn't be linear; it will be affine. So we basically have, if we model those M0, M1, and so on by vector bundles, we can think of those maps as really it's a tower of affine fibrations. So that's what it is.
Right. Thank you.
Sure. So this Q will be a cohomological tangent field. So a tangent field with degree 1, so it increases the degree of the sections it acts on, and it squares to 0. So it's a differential in a complex. Now this P stands for Poisson, but we will actually consider symplectic structures. So we will stay here in the non-degenerate world, and we will consider Q invariant symplectic structure omega of degree n, so the same degree as the degree of the whole manifold and the highest coordinate. Now let me give you a little more detailed. Yes.
One question: in the Poisson case,
yes,
you say, well, you think of this as non-degenerate, but you also need how do you deal with this? Because if you think of Poisson, you think you have a multi-vector field, right? You don't have a form.
Yes.
So how do you look at the Poisson structure then?
Well,
or it's the other way around, or it's formulated for Poisson structure and then you do the because it's formulated with forms.
Yes. Yeah. This is we define the structure as we start with the symplectic structure, and then we define the Poisson bracket quite analogously to the non-graded case, where we just have to be careful about some signs, but we basically just find the Hamiltonian function.
You mean that you have a notion of graded bracket, Poisson bracket somehow?
Yes, exactly. That's it.
Okay.
So this symplectic structure is the fact that I say that it has degree n means that it's homogeneous, and this inverts into a graded Poisson bracket.
Okay, thank you.
So the a more local picture, we can think of local coordinates and NQP manifold as this. We can think that they come in 4 types. The first, those xi's are just the ordinary coordinates of the base manifold M0. Those xi mu are graded coordinates which have non-zero degree, and here the word ghost refers to gauge field theories, where a completely analogous situation happens. We start with some non-graded fields, say bosonic gauge fields, and we add some new fields which acquire a grading, the so-called ghost degree, and those might be and here again the ghost degree comes with this graded commutativity. So those graded coordinates anti-commute whenever they are odd, and that's precisely what's happening in physics as well. And the last pair of coordinates are just conjugate to the first pair via the Poisson bracket, which is which comes from the symplectic structure. The cohomological tangent field now generates this cochain complex. So if we start with a section of degree 0, so function, it takes it to a degree 1 section. And in physics, we would say that we start from a bosonic field or a bosonic function and end up with a fermionic field. And so this Q increases.
Now it's when I'm going to ask you why this notation from physics. Pau and Pablo and myself are very interested in this. Well, Pablo, he cannot connect his microphone. So do you have, like, can you explain for people like us who don't know anything about physics, well, at least myself, why this notation?
Why this? Why do we extend this to those new ghost coordinates, or
why the notation? Because, well, I mean, it has to do with bosons, and I mean, why bosonic fermionic?
Oh yeah. Well, it's really just in the sense that bosonic objects are commutative and fermionic objects are super commutative.
Even degree, you always say it's bosonic, and fermionic it's odd degree.
Yes, here they do coincide. So this in physics, this degree, non-negative grading would correspond to this ghost degree, which counts how many levels of those auxiliary fields we added. And if we start from bosonic fields, so if we start from in the commutative case, then really odd, the parity in the ghost degree corresponds to the parity in the sense of commutativity and anti-commutativity.
Okay. Thank you.
Okay, so now there's another way to talk about this field Q. In this graded setting, such a field is always Hamiltonian. So there's always a section S of the structure sheaf such that it generates this Q via this graded Poisson bracket. And
so you mean that this chain of arrows is just doing like the bracket, this generalized bracket that you say with multi-vector fields or whatever. That's the arrow. I'm asking, like, Joaquin here. The Q is doing like the Poisson bracket with the object, or
yeah, the Q is doing the Poisson bracket with this S function. In physics, this S object would be in the action functional, but here we're in a finite dimensional setting, so it's just it's a section of our structure sheaf.
Okay.
And we have this lemma that says that the quadratic nilpotence of this Q translates to this equation which is called the classical master equation for S. So it in physics it somehow tells you whether this S is invariant with respect to change of the gauge. So this calculates gauge invariance. So let me just say a bit about the idea between the connection between fields and those finite dimensional manifolds. So in this AKAZ framework, that is to lift whatever geometric structures we need from finite dimensional source and target graded manifolds into a canonically defined space of fields. We can denote it map MN. Here I'm referring to this review paper of Catena and Schatz. And the basic idea is very simple. The maps would be the fields. But just to give you an idea that how the construction works, we choose such a such a graded manifold map Mn, which satisfies this property. This Cartesian product on the left-hand side on graded manifolds translates to stalk-wise tensor products. So this is a kind of tensor Hom adjunction. So we pick this kind of a notion of maps between graded manifolds that satisfies this kind of a adjunction, and then from that we go on and somehow lift the structures. I will not go into detail here. I just telling you that this framework exists, and this is what connects our finite dimensional calculations with what appears in physics. And in physics, we say differential, we mean equipped with a gauge transformation Q. So that's modeled by our cohomological tangent field. And we say it's symplectic. It translates to the physics jargon this way. The conjugate variables are called anti-fields. The graded Poisson structure, Poisson bracket, is called an anti-bracket. And this S function corresponds to the action functional, and again satisfies this master equation in physics. So this is the connection to gauge theories. And now let me go on to say a bit about how those NQP manifolds encode some interesting geometries in low degrees. So generalized geometry talks about Courant algebroids. A Courant algebroid is a vector bundle equipped with a fiber-wise pairing, a bracket and sections, and an anchor, which is a bundle map which maps sections to tangent fields. And a Courant algebroid satisfies the axioms of a Lie algebroid up to a kind of deformation, which is sort of measured by this pairing. So I would show you the axioms. I think that this version of the definition first appeared in this paper by Leo Weinstein and Xu. And I will not go through them. I will just show you that, for example, the first axiom is a sort of Leibniz-Jacobi identity, and so that does hold here, but the bracket is not anti-symmetric. Where in fact you can see that the axiom number 4 tells us how it measures the symmetry of the bracket. Now there's also an equivalent definition which say generates the same mathematics, where the bracket is in fact anti-symmetric. But when we do that, we lose this Jacobi-Leibniz identity. So it's kind of a trade-off. We always end up with something which is almost a algebroid, but not really. And now the idea is to how do we connect this with NQP manifolds? The idea is to define an NQP manifold.
Do you have an example in mind that doesn't of non-trivial example of Courant algebroid that doesn't satisfy this condition?
That doesn't satisfy which condition?
The condition of Jacobi.
Yes. Well, if we just take this bracket and anti-symmetrize it, that's what people call the usually this bracket is called the Dorfman bracket, and the anti-symmetrization is the Courant bracket. And this Courant bracket fails the Jacobi identity, and it's just much more complicated. But some of the other properties are nicer. So
but not one example that doesn't come as such, like one natural example where you have a Courant algebroid.
Okay. Well, I will come to an example. Well, the most natural example of a Courant algebroid is the standard Courant algebroid, which is just the direct sum of the tangent and the cotangent bundle.
Yeah.
The pairing
So a Dirac structure in a way. Okay.
Yeah. So here the bracket is defined by just Cartan calculus.
Okay.
And both the Courant bracket and the Dorfman bracket can be defined by ordinary operations, which you know from ordinary differential geometry, and and both of those brackets seem more natural in different contexts. But this one, the one which is symmetric and fails the Jacobi identity, is the one which is, for example, I think it's more used in the context of generalized complex geometry.
Yeah.
And there's this the PhD thesis of Marco Gualtieri, which is a standard reference for generalized complex geometry. There you can see this standard algebroid with the anti-symmetric bracket and the Jacobiator, which calculates the failure of the Jacobi identity, plays a central role here, So that's it.
This notation of Jacobiator is a notation of Weinstein, which looks very like Terminator. Probably he put it when there were all these films of Terminator 1, 3, and 4. Very nice. Yeah, I also think that the most natural example comes, at least in my mind, of Courant algebroid, comes from these examples of generalized complex. That's nice.
Yes.
Sorry for an interruption.
No problem. How do we connect this structure to an NQP manifold of degree 2? Well, we define the M0 part as the base manifold of the Courant algebroid. We define the M1 part as the total space of the vector bundle, where this one in the bracket denotes the degree shift. So we understand say the fiber coordinates as coordinates of degree 1. And now how about the degree 2 part? It's done via minimal symplectic realization, and it's specifically defined by this diagram as a pullback. And the very rough idea is that we're basically adding what we're adding here from what we're adding to M2, which is not in E1, are the momenta which are conjugate to the base manifold coordinates. And the way we do it is that we take this E plus E star, and there's this simple minimal symplectic realization, which is where upstairs the only thing which is upstairs and is absent downstairs are precisely the momenta conjugate to the base manifold coordinates. So this is what we're kind of adding when we're going upstairs, and we want to transfer this to this E1 part, because that's one our M1 part is just this E, the Courant algebroid, and the way we do it. So what's so this map on the right, which goes downstairs. So that's just the projection where we forget about the momenta, and this map from E to this sum is this isometric embedding. So I say isometric, I mean that E comes with this pairing, it's a Courant algebroid, and this E plus E star, there we take the pairing defined naturally by the duality between E and E star. So we just let the elements act on each other and then sum it up. And can be shown that this isometric embedding downstairs translates to a symplectic submanifold here, symplectic submanifold upstairs. So M2 turns out to be a symplectic submanifold of this D star E, and it turns out to be a minimal symplectic realization of E as well. So it's a somehow universal map, universal Poisson map from this symplectic manifold M2 to this Poisson manifold E, where again you may wonder why I say that E or E1 is Poisson if it's just this vector bundle with a pairing, but the idea is that this degree shift actually adds a sign and turns this pairing into a Poisson bracket, as we will see on the next slide again. And here you may realize that we haven't used any of the differential structure, the Q field or the bracket and the anchor. And really this is a theorem that works just for on the level of vector bundles with a pairing. So pseudo Euclidean vector bundles, we consider arbitrary signatures, just symmetric, non-degenerate pairings. And this corresponds to NP manifolds of degree 2. So N manifolds with this symplectic, homogeneous symplectic structure. And this bijection, this correspondence only works on isomorphism classes, because if we want to construct an NP manifold by taking sort of modeling the sections of the structure sheaf as sections on a vector bundle, we need to use the Bachelor's theorem for N manifolds, which is a version of the Bachelor's theorem in supergeometry, which says precisely that we can model supermanifolds or N manifolds by a bunch of vector bundles, but this correspondence is not canonical. So whenever we use this theorem, we can only talk up to isomorphism. And similarly, for NQP manifolds of degree 2 and Courant algebroids, we have this one-to-one correspondence on isomorphism classes. So this is the this main theorem of Roytenberg. And let me just sketch the proof. The point is that in degree 2, our Hamiltonian function S always takes this form. And the reason is just degree counting, because this Hamiltonian function necessarily has degree 3. And now those rho and c are structure constants with degree 0. This 1/6 is just for some technical reasons. Those xi's are local coordinates, or local generators of this M algebra of degree 1, and this P has degree 2. And the degrees add upon multiplication. So the first term is of total degree 3, and the second one as well. And those two are the only combinations of the local coordinates that make up this a function of degree 3. So here we can see that if we allowed negative degrees together with non-negative degrees, it would be much more complicated, because we could always multiply something with a we would have an infinite amount of combinations. So that would make it much more complicated, and we would need to work with formal sequences of sections. So this is one of the reasons why non-negative graded manifolds are much easier to work with. And now we can just use those structure constants, and we can see that here should be the Poisson brackets. The Poisson bracket and S on the NQP manifold correspond to the Courant algebraic operations. So first, the pairing, fiberwise pairing, should correspond to the Poisson bracket. So you might say that, well, the pairing is symmetric, but the Poisson bracket is antisymmetric, and it really is antisymmetric in this in degree 2. But it's here we restrict it on sections of degree 1. Those thetas are of degree 1. So the anti-commutativity in odd degree adds sign So now both sides of the equation are symmetric, and this makes sense. And similarly, we require this bracket of the Courant algebroid to acquire those structure constants, and similarly for the anchor. So that's the rough idea, and then the most technical part is to show that those operations do indeed satisfy the Courant algebroid axioms if and only if this master equation holds. And I can show you the expression for the bracket of S with itself. I won't go through it in detail, but just to give you an idea, for example, this third term, you could guess that it's 0 precisely if this part is 0, the Leibniz-Jacobi identity here, if that's satisfied. So these terms correspond to some of the axioms, and other of the axioms are automatic from the construction. Okay, so this is the theorem, and now we can ask whether we can extend it to morphisms as well, to equivalence of categories maybe. And the way to do this properly is to consider relations. So let me start with substructures of Courant algebroids and NQP manifolds. So because we will need them to define relations. So a Dirac structure is a subbundle of a Courant algebroid supported on a closed submanifold. And this Dirac structure is isotropic with respect to the pairing. So the pairing vanishes on it. It's involutive with respect to the bracket. So if two sections take values in the subbundle, if we restrict them onto the submanifold S, then their bracket will have the same property. And also this Dirac structure should be compatible with this row, with this bundle map. So now a nice example is generalized complex geometry. There are certain Dirac structures of standard Courant algebroid, which is just this direct sum of the tangent and cotangent bundle, generalize and interpolate complex and symplectic structure on this base manifold. And those Dirac structures are basically the plus minus I eigenbundles of a complex structure on this Taylor space, on this Tm plus T star m, with the extra property then that it's compatible with this natural pairing and with this natural bracket.
I have a silly question. If we consider a Jacobi structure, can we put it in your scheme, or it's in another? It wouldn't fit your scheme. Can we define a Jacobi structure as a Courant algebroid, or it doesn't enter here?
Sorry, I'm not sure what we define as a Jacobi structure.
So Jacobi structure would be like the equivalent. So as symplectic is to Poisson, let's say, the equivalent Jacobi structure would be the generalization of contact structure, but it includes, you may have a foliation which is not necessarily symplectic. You may have odd and even dimensional leaves. So it's more general than contact. And so I think it doesn't quite enter this scheme, but probably there is an analog construction that you can do. I think, there are papers, I should check it out, because there are a student of Marius who has been working on this Jacobi structure. So I think there is a way to put the Jacobi in another category, which is not Courant algebroid. Maybe it's called Jacobi. I don't know. Let me check. Well, in any case, I was just like, it's out of my mind question. Maybe it's not related to this talk. It's to know. I think like it's to know, like, your scheme is very general. It's to know if your scheme covers in a way contact geometry, which I think it doesn't. I think it covers everything, quite a lot of things in Poisson and symplectic, but not so the Jacobi or contact part. And then probably somebody has done a kind of, analog for the contact. I don't know. I should check it out. Usually, contact things are less popular when you try to do the OID part, because the people in contact geometry believe everything is contact topology, and then if you do not do this contact topology, you are out of the game somehow. Well, it was a question just for to put order of ideas, like where this box enters. Well, okay, sorry.
Yeah, sure. It's a so never encountered those structures in this setting. So that's a good question. And just the reference is Gualtieri 2004, which is that's the PhD thesis, which is it's a very, very nice read. And once we're talking about this standard algebroid, you can say that it corresponds to this NQP manifold, which is given by this shifted vector bundle. Okay, well, now we can do a similar thing for NQP manifolds, and a dg-Lagrangian submanifold will be a half-dimensional closed submanifold, such that it's a Lagrangian, so the symplectic structure vanishes on it, and this S Hamiltonian function vanishes as well. So that's the dg part. And now an example from gauge theory is that gauge fixing actually chooses a dg-Lagrangian submanifold. And in physics, we would denote it maybe like this. We would say that the anti-fields, phi star, so those would be the conjugate fields. We fix them, so we fix the half of the coordinates by requiring them to be derivatives of this f, a gauge fixing fermion with respect to those phi's. So they're conjugate fields. So that's how it appears in gauge theories. And now a key theorem is to see whether those are those correspond to each other, and the answer is that they do. That for a Courant algebroid E and symplectic realization with all the induced structure M, which you talked about in the context of Roytenberg's theorem. In these settings, Dirac structures on E are actually in a bijective correspondence with dg-Lagrangian submanifolds of M, and this other M should be this fancy M of the NQP manifold. And just a very rough idea of the proof. So the idea due to Gritzmann is to take the Dirac structure, the subbundle of E, and again we need to add something. We need to basically add some momenta to add the M2 part, so to say, and we do it by considering the conormal subbundle and some appropriate degree shifts again. And the idea is that we basically add as many momenta as we can, so that it stays Lagrangian. Because in the sense that if we added too many momenta in a given basis, then we might end up with a conjugate pair in our submanifold L. But once we have a conjugate pair, then the Poisson bracket gives something non-trivial, and it's not Lagrangian anymore. So it's like fitting in as much momenta as we can, and it's easy to see that indeed L is isotropic with respect to the Courant algebroid pairing, if and only if L is Lagrangian. and it's let me just remind you that this Lagrangian submanifold is really Lagrangian in the sense that it has the half of the dimension, but this L submanifold doesn't need to be that way, and and this conormal subbundle is precisely what makes it like if we're what compensates for the lack of dimensions. So we have something that's not necessarily even maximally isotropic, and we translate it to something which is maximally isotropic and Lagrangian. So that's an interesting thing. And now to the differential structure. So it can be done locally in coordinates, and we can prove that this Hamiltonian function S vanishes on L if and only if those two terms do. And the first one vanishes precisely when this L is compatible with the Courant algebroid anchor, this vector bundle map, and the other part vanishes again if and only if the Dirac structure is involved with respect to this Courant algebroid bracket. And so this proof is quite straightforward, but we need to use some non-trivial properties of Courant algebroids to actually see this work. And this in the original theorem of Gritzmann, it was a little less general. He considered a situation where this row compatibility was kind of automatic, and he used used properties of derived brackets to show that the involutiveness corresponds to S vanishing in this a little less general situation. But here I want to show you that it's easy to show in coordinates, and it gives you this more general picture actually, and also it might be a good setting for a generalization to higher degrees where we have just more terms with more structure constants. And the last part is to check the surjectivity of this assignment, where when we take the Dirac structure L and turn it into this Lagrangian submanifold, we are extending it somehow. So it's injectivity is very simple to see, and surjectivity holds as well. So indeed, Dirac structures are in a bijection with dg-Lagrangian submanifolds, and this will be important later to prove that there's actually an equivalence of categories.
So in this mirror that you are constructing,
Mm-hmm.
if you go to this right side,
Mm-hmm.
instead of taking the dg-Lagrangian, you take the case of Lagrangian submanifolds, you take isotropic or coisotropic. What is the analog?
Yeah, that's a good question. Yeah, now I don't know.
That's a natural question, right? Because
yes.
that would be very interesting
Mm-hmm.
indeed.
Mm-hmm.
That's good.
Yes.
That's
Now this yes, because this like for now we're in degree 2 and in degree 1, the again, what would be the left hand side would be some substructures of Poisson manifolds, and those would be coisotropic submanifolds.
maybe it's easy to start with the isotropic one, because the second condition, let's say you have part of the conditions, but you don't have all of them. So it has to be a bit more general for the DG side. I don't know. I don't know. It's a natural question, right? Because it's like it puts things in the picture.
Yes. So this would be if it was just isotropic, then it would mean that you would need to when going from the Dirac structure to the submanifold, we need to add just some of the momenta, maybe not all of them.
Exactly.
So yeah, it will be some kind of this partial construction.
So then you don't have, let's say, you cannot have like the DG. You cannot have the Dirac case. You have to have a subclass, which I don't know the name, but maybe it's possible to identify. I don't know.
Yeah.
In any case, very interesting.
Yes. So that's an interesting question. Yeah. So this is our theorem of the correspondence between the substructures, and we will translate it to bijection on morphisms later. So now, how do we define the morphisms? So this idea, I think it's due to Weinstein, and here I'm referring to this those lecture notes from 2010, which are very nice. And the idea is to if we want to define a symplectic category, we might the naive idea would be to take just symplectic morphisms, which are morphisms that do preserve the symplectic structure. But of course, those are very, very strict because they need to be diffeomorphic. Then all of the then we'd all need to consider just diffeomorphic manifolds, and we couldn't talk about, for example, symplectic reductions and other interesting things. So the remedy is to consider Lagrangian submanifolds of the product of the two manifolds. And we can do an analogous thing in the world of Dirac structures and Courant algebroids. And it was done by Vilkovisky. And we can define Dirac relations, Dirac relation from E to E prime as a Dirac structure R of this product Courant algebroid. Here I will sort of switch the direction. I will go from right to left, because later there will be diagrams where this right to left composition is the composition in the diagrams will correspond to the composition of the algebraic composition. So that's why I'm switching switching it this way now. And it's supported on, again, the product of those submanifolds. And now, and this bar denotes a Courant algebroid with a pairing where we take the opposite degree. So that's just opposite sign. So just a technical detail. Very interesting. Now some examples. The first example is a graph of a structure preserving bundle morphism. So that's the basic example. What we really want to be included in our category. But we can see that, and it really there's really a theorem that says that Dirac relations actually correspond to morphisms that do preserve all the structure, or the bracket, the pairing, and the anchor. Now, some more interesting examples include symplectic reduction, but also some reductions in the Poisson role. Like, for example, if you take a Poisson bracket and what is it called, second class constraints, you end up and you apply a reduction procedure, say a Dirac reduction procedure. You end up with the so-called Dirac bracket. So that's again something which is known from gauge theory, string theory, and it's really just analogous to symplectic reduction, but done in this Dirac, in this world of Courant algebroids and Dirac structures and generalized geometry. And then also there's this very interesting example of Poisson-Lie T-duality, which is a some sort of relationship between two string theories, where we can model it by Courant algebroids, and a direct relation between them, which again cannot be modeled by a bundle morphism. Now we can do the same thing for NQP manifolds and define a dg-Lagrangian relation. Again, be a dg-Lagrangian submanifold R of the product, where the induced symplectic structure and the Hamiltonian function S vanish. And the way we induce them on the product is that we take we pull them back to the product, and we basically compare them on this correspondence space. So whenever those differences vanish, means that they are those omega n and omega m are related, and those Sn and Sm are related. Now, how do we compose those relations? So I will give you just a brief idea of what we would like to do, and then I will tell you when it really works. So let's say we have two relations, R, which goes from M to M primed, given by this submanifold R, and R primed, which is given by this submanifold R primed. So these squiggly lines are just formally denote the relations. Now, out of those two, we want to construct a third relation, a submanifold of this product of M double primed and N. So how do we do that? We want to the new relation to somehow encapsulate information from R primed and R, but so that it coincides on M prime. So we might want to take a limit of this diagram, a fiber product over M prime, basically. Now, this may or may not exist in the category that we're working on, but for this moment, let's just continue. And because even if it does, this object here, R prime diamond R, contains all the information that we need, and the information from R and R prime does coincide on M prime, but it's not a submanifold of this M double prime times M. But here we can just take the canonical map to the product, such that it commutes commutes with those maps that go from R prime diamond R to those M double prime and N. And if we take this map, then we can define the composition as the image of this map. So data. So this P composed with this inclusion is the canonical map to the product, and we take this R prime composed with R is the image. Again, the image of this map might not be an object in our category. So we may ask, when does this construction work? And in the world of generalized geometry, it was proven by Jan Vysocký that certain transversality conditions on this R prime diamond R and this projection P must be met, and then R prime composed with R is really a well-defined direct relation. And we can sort of copy this for NQP manifolds. We can let me just show this technical lemma, which says that here the differential structure again transfers from it composes well. So if two Hamiltonian functions are related between M and M primed, and between M primed and M double primed, that then you have we really have a relation between the first one and the third one. So let me just say it this way and move on. And given this setting. So see, we have objects and relations which sometimes do compose and sometimes don't, and we have the conditions when they do. We define a correspondence as an equivalence class of sequences of relations. So we take such a sequence, and we define a Wareheim-Woodward category where the composition is given just by formal concatenation of those sequences, and the equivalence relation is this one. We consider a pair to be equivalent to this singleton, where we have just this one relation. We compose those two relations whenever the transversality conditions are satisfied. So then we can compose them and can actually define this one relations from those two. And this way we have just a now, of course, there's this large theory behind Wareheim-Woodward categories, and is something that I don't know much about, and I won't go there. So I'm just really using them as a tool to it's a very simple tool to encapsulate all the data and talk about Courant algebroids and NQP manifolds in a categorical way. So now we have well-defined categories of Courant algebroids together with correspondences, and NQP manifolds together with correspondences, and in particular we have the category of Courant algebroids of degree 2. And we might ask whether those two are indeed equivalent, and they are. We have actually seen the equivalence already, because on objects we have this theorem of Roytenberg, which says that Courant algebroids translate to NQP manifolds of degree 2 via this minimal symplectic realization and all this induced structure. And this assignment is essentially subjective because it works on isomorphism classes. And on morphisms, which are now correspondences, we can use our theorem, generalization of this theorem of Gritzmann, because we know that Dirac structures are in bijection with dg-Lagrangian submanifolds via this construction of this conormal subbundle. And we can use this for each component of a correspondence. So a correspondence consists of those relations, and each relation is really just either a Dirac structure in this product Courant algebroid, or a dg-Lagrangian submanifold in this product NQP manifold. And on each of them we can use this bijection, and we end up with a bijection of those whole correspondences. So we have this assignment, which is this functorial assignment, which is essentially subjective on objects and bijective on morphisms, and so that it's a fully faithful, essentially subjective functor, and that forms an equivalence of categories, provided we have axiom of choice, which I hope we do. And so this is the main result, is that we can stitch together the theorems and some theorems and lemmas from the last year to show that those two worlds are actually equivalent in this categorical way. And as a concluding remark, let me just mention the so-called quantum odd symplectic category. And the idea is that, okay, we define OSC, odd symplectic category, to be just the category composed of NP manifolds in odd degrees, together with correspondences. And the claim is that this is, in a way, a minimal quantization category, in the way that all quantization functors which satisfy certain conditions factor through this category. So what does that mean? Well, an example of such a quantization functor is given by Ševera in this paper from 2006. And he defines it on this odd symplectic category as an identity on objects and on morphisms. We take a relation, we take a correspondence, and for each of the relations, we map it to a Dirac delta function, or a delta measure supported on this submanifold, and we consider it as an element and as a semi-density. So it should transform in a certain way. So we may think of it as a Dirac delta tensor with a semi-density. And now for those objects, how do we define composition in this target category, this quantum odd symplectic category? Well, composition of those two Dirac deltas is given by now informally written by integrating over this M prime manifold. So we have those. So it's like the second one, the one where we concatenate those relations, and we just integrate over those extra dimensions. And now we can again ask, okay, given that our integrals are well defined, isn't there any problem with transversality and so on? And there is, but provided that we have the transversality conditions for that we had before are met, then this integration, this composition really is well defined again, or more precisely, if we choose correct test functions, and if our integration is well defined, then composition doesn't mess it up. So that's the point. And now, with respect to, if we consider functors of this form, which end up land in a category where we need those transversality conditions, then of course that taking our Verheim-Woodward category is really a construction of correspondences with the minimal amount of data that translate to those to be quantum categories. And let me just very briefly mention why even use this word quantum here. It's related to BV quantization, again, which is relevant in gauge theories, because in this quantum odd symplectic category, or even in this odd symplectic category, we have a canonical BV Laplacian. So that's an operator which can be defined locally in a Darboux chart, but it can be shown that it's actually invariant with respect to Hamiltonian diffeomorphisms. So it's really defined canonically for the whole manifold, and it satisfies this. We have this kind of compatibility for this alpha, just closed with respect to this operator. So it's actually again a differential and a complex, and it for this closed object, so closed semi-densities it acts on, we have this kind of gauge invariance, which says that basically integrating over this R submanifold is the same thing as integrating over this deformed submanifold. In gauge theory, the choice of this submanifold corresponds to the choice of gauge fixing. So really, it says that integrals of this form, which are central in gauge field theory, do not depend on choice of the gauge. And in field theory, those require the form of formal path integrals, and what we're integrating is our action functional and so on. But the point is that we can actually translate it to a rigorous statement in a finite dimension, and this odd symplectic category is simply equipped with this canonical structure, and and we have this gauge invariance, which really is the one condition that that we need to start quantizing gauge theories and start with this whole process of renormalization and so on. So here, let me refer to this paper by Kudaverdian from year 2004, where there are details about how those odd symplectic manifolds and those BV Laplacians work, and what is the actual geometric intuition behind this BV Laplacian. So this is the quantum origin. Comes from BV quantization, BV path integral quantization in field theories. Okay, so that was all I wanted to say. So that just fast remarks about the possible outlooks. So what I'm trying to understand now is whether these correspondences can be used in the context of quantum homotopy Lie algebras, and if they can illuminate maybe some of the constructions in the context of the homological perturbation lemma. So it's a very nice theorem which says that basically what physicists have been doing can be formalized in a homological way, and quantum homotopy Lie algebras are very, very close to NQP manifolds. So the question is if we can generalize our correspondences, and if then we can say something interesting about what we get there. Another idea that I might hopefully get to is our bundle gerbs on N manifolds and NQP manifolds, because we may start analogously to construction on several manifolds due to Huerta done last year. So we may do the same thing and ask whether what are the conditions of the structure of bundle gerbs being somehow compatible with the Q and P structures. And finally, this is a question here for you, if we can talk about B and QP geometry. So maybe if we can start with B symplectic graded manifolds and ask what they
we should do this before somebody else does it.
Yeah. So this is a very natural question.
I had already thought about that, because you can do this dg correspondence like in the symplectic case in the same way. So you have naturally a notion of bisymplectic. But what I think it would be interesting is the quantization connection. Yeah. But sorry, you didn't finish. I have questions, but I want you to finish first.
Well,
you have another item to show, I think.
Yeah, and the last item is thank you for your attention. So okay. Yeah, thank you for your attention.
You are quite welcome.
Thank you.
Thank you, Martin. So now let's, as we have seen, there are some questions from Eva. Now it's the moment that you can ask questions, Eva, or everyone, to Martin.
Thank you, Pau, for telling me. I've been talking too much, but well, of course, a natural question is the B correspondence and so on. But there are some other questions in the way because, there are a lot of people working on those objects at this moment, right? And you connected somehow to the motivation of the thesis of Marco, but you can push it a little bit farther in two different ways, this connection. On one hand, in his dictionary, once you have this generalized complex, you have this decomposition where you have a Poisson part. And there you can also assume that this Poisson part is of B type. This is a different question than the one you are asking. It's two different questions related. And then the context in which you end up, and this is something that was proved by Galtieri and Cavalcanti, is Calabi-Yau, which is very interesting. Okay. And then the other question is the connections to quantization. Well, indeed, I have two questions. Connections to quantization, you are telling us about a type of quantization, but there are, of course, others. And one of them was already attempted by Marco himself with one of his, former students, now postdoc in Oxford, which uses the notion of brains in this generalized complex. And I don't know if you had a chance to look at that paper. It's a paper with Biskov and Bischoff and Galtieri. Maybe it's already from the pre-pandemics, because I don't know. Maybe it's 2019.
Yeah, it's familiar to me, but I haven't really got into it. But I know about those connections. So that's so this is like another exciting topic, and then I'm thinking whether So I don't know anything more specific.
Yeah. Well, all these are interesting connections that we could try to explore. I mean, if you get this ground and you come here, indeed, this is a good starting point. And of course, the connection to quantization, which is something in which other people in the lab are working, like Pau is working on this. The last question that I have is that when you say gauge, we say gauge, and everyone, gauge theories. So gauge, it means that you have some kind of transformations of a bundle, right?
Yes.
And when you say gauge here, the bundle that you consider in all these bundles, which one is the bundle?
Yes. Well, it's so the idea is that and engage in this BV-BRST framework. We start with some vector bundle with an action of a Lie group, and we have those gauge fields which are just we can think of as just just the connection one form.
Yeah.
And this whole BV-BRST idea. So maybe I can go back to this slide. Is okay. So it's in this coordinate picture. We start with those. Here we have those ordinary coordinates xi. When in gauge theories, we start with those gauge fields, and we are adding those new fields. We're extending our space of fields. So it's a mathematically it will be a homological resolution, because the gauge transformation on our original gauge fields now extends precisely to this cohomological tangent field. So this Q really plays the role of gauge transformation.
Okay.
And this master equation that says that the bracket of S with itself is 0. So that's really the gauge invariance of this S. So it says whether our dynamics are invariant with respect to the gauge, and really the zeroth cohomology of this Q operator corresponds to classes of gauge invariant say action functionals. So really it's a So really, I mean this Q operator, and by gauge invariance, I kind of mean, yeah, it's always something a bit different, but really some kind of compatibility with it.
And here, well, I mean, you have showed all the computations in local coordinates, right? But you are talking about cochain complex, so the topology has to play a role.
Yes.
You have kind of global computations of these cochain complexes. I mean, quantization, they have to be relevant.
Well, yeah, they might. Yeah, they in this BVBRST setting, we might encounter anomalies, and those anomalies are precisely the where the topology of say
Non-trivial topology.
Yeah, but
I love physics because then you have all these fancy names: bosonic, fermionic, anomalies.
Yeah. So an anomaly.
Much more attractive in any case.
Yeah, we just really just what we get when we're integrating over. Yes, now I'm trying to not say those words from this terrible physics jargon, but really.
No, I mean, it's good. I mean, it's good. I mean, it's good to understand the connection.
That's very
rich. So.
Yeah, so it's really so like in the in the standard model we might get this I get like instantons which come just from which are really just this kind of a winding number of our gauge transformation in some sense. So those do play a role, and in physics they call them anomalies.
Yeah. Okay, that's nice. I don't have more questions. I made a lot of questions. I think maybe Robert looks like he wants to add something.
No. I don't have questions.
So if no one has more questions, let's thank Martin again, and let's hope we see you at some point, maybe in person.